Hello students. So already in the last class, so in the last lecture we have come across the different types of interests which are available in 8051. So basically we say that there are 6 different types of reset, means by considering the reset as one type of an interrupt, because when the reset signal is applied, the normal working or the normal execution of the program will be terminated, but just by considering the reset as one type of an interrupt, we can say that in 8051 it has 6 different types of interrupts. They are your reset, external interrupt 0, that is int 0, timer 0 overflow flag interrupt, external interrupt 1, timer 1 overflow flag interrupt, and the serial communication interrupt. So upon reset all the registers are cleared, means in other terms we can say that upon reset, as all the registers are cleared, all the interrupts are disabled, and the microcontroller, it does not respond to any of the interrupts. So if the microcontroller has to respond to any of your interrupts, then the interrupts after reset, they have to be enabled by software. They have to be enabled by software, and this is done by programming or configuring the interrupt enable register, which is an 8-bit register. Okay, so before beginning with your the register IE, interrupt enable register, so just we'll have a quick glance over okay, what are the different methods which are adopted for servicing the external devices which are connected to your 8051C. So basically there are 2 different types of techniques which are used. One is the interrupt method and the second one is the polling method. Okay, so in case of your interrupt, the priority levels can be assigned, means the which interrupt has to be, if multiple interrupts occur at the same time, then which interrupt has to be serviced first, whereas in polling the priority cannot be assigned, right? So in case of your interrupt, the device is attended, means the service is provided only when it makes a request. But in case of your polling method, so after a specific duration of time, or we can say after executing each instruction, it will check all the devices in a round robin fashion, that is a ring fashion. Okay, so then after checking all the devices, means it will monitor the status of different devices which are connected to it. If any of the services, if any of the devices, if they make a request, or if they require a service, then the service will be provided, right? So in case of your interrupt, a particular interrupt can be masked, means the interrupt either it can be enabled or it can be disabled. If it has been masked or disabled, then the interrupt will not be serviced. But in case of your polling method, there is no any masking facility available, right? So in case of your interrupt method, it makes the efficient use of the microcontroller's time, whereas in case of your polling method, the time is wasted, because even if the microcontroller does not require, if the external device does not require the service of your microcontroller, the microcontroller will keep on checking it, right? Then difference between your ISR and subroutine, interrupt service routine and subroutine. So ISR is initiated by a hardware such as a timer or serial port, whereas your subroutine is initiated by a program. So ISR is invoked when an interrupt is getting service, means ISR is invoked, means the ISR is executed when an interrupt occurs, whereas your subroutine, okay, is executed as per the programmer's view, right? So every interrupt has a fixed ISR, whereas your subroutine is written to make a program modular, right? So ISR is stored at a fixed ROM location. A subroutine is stored along with the main memory in the secondary storage, right? An interrupt factor table stores the addresses of all the serviceable interrupts, whereas your subroutine, it gets loaded during the execution of the program. So all the ISRs, so whenever it has to branch or service the ISR, then it makes a long time jump, whereas in case of subroutine, it can be used by the programmers and is also subjected to change. ISRs cannot be altered by users, whereas in case of subroutine, there is no limit to a number of subroutines in a program. The number of ISRs inside a ROM is fixed, whereas subroutine names are identifiers, right? So coming back to your interrupts, so the interrupts, they're having a fixed memory location. So whenever the interrupt occurs, then the microcontroller, it knows where to branch, means from which memory location the instructions have to be executed. Okay, that is which memory location the instructions have to be executed, and these memory locations commonly we call it as the interrupt factor table. So if the interrupt occurs, then the microcontroller branches to the vector address or to the memory location in the ROM memory, that is 0000. If it is external hardware interrupt 0, that is INT 0, then it branches to memory location 0003. If it is a timer 0 overflow flag interrupt, that is TF0, then it branches to memory location 000B, right? So if it is an external interrupt one, that is INT1, then it branches to a fixed memory location, that is 0013 in the internal in the ROM memory. If it is a timer 1 overflow flag interrupt, that is TF1, then it branches to memory location 001B. If it is a serial communication interrupt, either it may be RI or TI, then it branches to a fixed memory location in the ROM memory, that is having the address 0023, right? So what are the steps involved in executing an interrupt, right? So first it finishes the instruction it is executing, saves the address of the next instruction, that is the content of your PC on the stack memory. Next, it also saves the current status of all the interrupts internally. Means if any of the whatever the content of your interrupt, the status of your interrupt is there, it will be preserved. Okay, then it jumps to a fixed memory location and branches to a fixed memory location in the memory called as interrupt factor table and holds the address of the ISR. Right. Next, the microcontroller gets the address of the ISR from the interrupt factor table and jumps to it. It starts to execute the ISR until it reaches the last instruction in the ISR. So always in case of your ISR, the last instruction will be RETI, return from interrupt. Upon executing RETI instruction, the microcontroller returns to the point where the original program was interrupted. Means whatever the return address which was preserved on the stack memory will be loaded back into your register PC, and then the microcontroller resumes the execution of the main program or the interrupted program, right? So these are some of the steps which are taken by your microcontroller when the interrupt occurs, right? So next, so then we have our interrupt enable register, that is the interrupt enable special function register. So I is a 8-bit register. Out of your 8 bits, okay, out of your 8 bits, 6 bits have been defined. So the MSB bit labeled as EA, okay, that is your interrupt enable interrupt bit. So it is cleared to 0 by a program to disable all the interrupts. Means if we enable interrupt, if EA is disabled, then all the interrupts will be disabled, and it is set to 1 to permit individual interrupts to be enabled by their enable bits. Then bit number 6, which is undefined in 8051, it is not implemented, the user should not write anything to it. Then bit number 5 labeled as ET2, it is not available in 8051, it has been resolved for the future use. Then you have bit number 4 labeled as ES, enable serial port interrupt, enable serial port interrupt. So if the ES bit, if it is set to 1 by a program, it is set to 1 by a program to enable serial port interrupt, and it is cleared to 0 to disable serial port interrupt. Then you have bit number 3 labeled as ET1, enable timer 1 overflow interrupt. It is set to 1 by a program to enable timer 1 overflow interrupt, and it is cleared to 0 to disable timer 1 overflow interrupt. Then you have EX1, enable external interrupt 1. It is set to 1 to program to enable INT1 interrupt and cleared to 0 to disable INT1 interrupt. Then you have bit number 1 labeled as ET0, enable timer 0 overflow interrupt, set to 1 by a program to enable timer 0 overflow interrupt, and it is cleared to 0 to disable timer 0 overflow interrupt. And bit 0, that is a LSB bit labeled as EX0, okay, enable external interrupt 0, set to 1 by a program to enable INT0 interrupt, cleared to 0 to disable INT0 interrupt, right? So if you have a quick glance, the MSB bit labeled as EA, it is used to enable or disable the interrupts. So if it is made as 0, then all the interrupts, irrespective whatever the status it may be of your external interrupt or serial communication interrupt or your timer interrupt, Okay, whatever may be the status of those bits, all the interrupts will be disabled. So if you want to enable the interrupts, then first the EA bit has to be made as 1. Then by enabling the remaining bits, the individual interrupts can be enabled or disabled. So if the bits are set to 1, then the interrupts will be enabled. If the bits are set to 0, then the interrupts will be disabled. Okay, and IE is a bit addressable register. Then you have the next register like interrupt priority register, which is a special function register. So out of your 8 bits, okay, 5 bits have been defined in 8051. So bit number, the MSB bit, that is bit number 7 and bit number 6, they are undefined. Bit number 5 labeled as PT2, which is reserved. Okay, currently it is not available in 8051. The feature has been reserved. Bit number 4 labeled as PS, priority of serial port interrupt set or cleared by the program. Okay, then bit number 3 labeled as PT1, priority of timer 1 overflow interrupt set or cleared by program. Bit number 2 PX1, priority of external interrupt 1. Bit number 1 labeled as PT0, priority of timer 0 overflow flag interrupt. Bit the LSB bit, that is bit 0 labeled as PX0, priority of external interrupt 0. Okay, so if any of these bits, okay, either it may be your serial port interrupt or timer 1 overflow flag interrupt or external interrupt 1, or your timer 0 overflow flag interrupt or external interrupt 0. Okay, so by setting any of these bits to 1, then the priority will be at the highest order, and if the bits are made as 0, then the priority will be the lowest. So accordingly, by configuring the appropriate bits, the priority levels can be assigned, whether it is having the highest priority or it will be having the lowest priority level. Okay, and your register IP, that is your interrupt priority register, it is a bit addressable register, 8-bit bit addressable register. Okay, so next coming to method of enabling only timer registers and disabling others. So if you want to enable only the timer interrupts and disable the remaining, either it may be your serial communication interrupt or it may be the external interrupts, first the bit D7, that is the MSB bit of your IE register, that is bit EA of your IE register, it has to be set to 1. Then okay, enable ET0 bit in the IE register, that is a bit 1 of your IE register, it has to be set to 1. And then enable ET1 bit in the IE register. Okay, whereas the remaining bits, they have to be made as 0. They have to be made as 0. For example, you can say move A8. Okay, that is the A8 is the address of your IE register. A8 is the address of the IE register. Okay, copy 00 into A8. All the registers will be cleared. Okay, all the interrupts will be disabled. The IE register has been cleared. Then set bit IE.7, as we said earlier, it is a bit addressable register. The MSB bit will be set to 1, which indicates that now the interrupts have to be enabled. Now the other bits of your IE register have to be configured. Then set bit IE.1, which indicates that ET0 of your IE register. Okay, that is our timer 0 overflow flag interrupt. Now it will be set to 1. Okay, then set bit IE.3 means set the timer 1 overflow flag interrupt, the timer 1 overflow flag enable bit to 1. Okay, so then the next example you have method of enabling only external hardware interrupts and disabling others. First the IE bit, EA bit, enable all. Okay, the MSB bit of your IE register, it has to be made as 1. Then IE.0, that is EX0 bit in the IE register, it has to be set. Then EX1 bit in the IE register, it has to be set, and it can be done by using the instructions like set bit IE.7, set bit IE.0 and set bit IE.2. Okay, so whenever you want to return from main program, means from your subroutine or the interrupt service routine. Okay, so if you want to return it back to your main program, there are two different types of instructions, that is return and RETI, return from interrupt. So basically for the user defined functions or your procedures or the sub programs, Okay, returning to the main program is to the calling program. It is done with the help of RET, that is return, right? So always RET, it has to be the last instruction of your subprogram or a procedure, whereas RETI, it has to be the last instruction of the ISR. Okay, so RET instruction is used to return from a subroutine to previously called by long call or absolute call, that is L call or A call. RETI is used to return from an interrupt service routine. RETI first enables interrupts of equal and lower priorities to the interrupt that is terminating, whereas your RET program execution continues at the address that is calculated by popping the topmost 2 bytes of the stack. The most significant byte is popped off the stack first, followed by least significant byte. But in case of your RETI, program execution continues at the address that is calculated by popping the topmost 2 bytes of the stack. The most significant byte is popped off the stack first, followed by least significant byte. Okay. In RET, that is return, a return from subroutine will pop only the return address. But in case of RETI, a return from interrupt will pop the flags and then the return address. Okay. Thank you.